So this is how to determine the deflection as in case of overhanging beam. So we need to determine the deflection as in case of overhanging beam using the unit load method. So here I have taken a overhanging beam. So here as a separate entity, it is called as cantilever part. So the distance of BC is equal to 2 meters, and you have the overall load as equal to 45 kilonewton meter. Overall load as equal to 45 kilonewton meter between A to C, and then you have the moment of inertia as 2I between A to B and I between B to C. So this is the overall question which is given, and they have asking to find out what is the value of the deflection at free end. So here free end is at C itself. Free end is at C itself. So now here basically before calculating the deflection, so here in the previous problem we have solved for the cantilever beam, wherein there were no consideration of the support reactions. But here, since it is a simply supported part wherein we are supposed to calculate the support reactions for the effective solution of the deflection. So therefore 45 kilonewton meter is the load which is there. So for this 45 kilonewton, first I need to calculate what is the support reaction for this real load of 45 kilonewton per meter, that is UDL. So I just apply the equilibrium conditions. So as you all know that there are three equilibrium conditions. So first equilibrium condition is that sigma h is equal to 0. So since there is no horizontal forces over here, so automatically that equilibrium condition will be satisfied. So second equilibrium condition is sigma v. So sigma v, I have taken upward forces as positive and downward force as negative. So with this sign convention, if I proceed it, so this is VA and this is VB. So both are going in the upward direction, hence it is considered to be as positive. And then we need to convert this load into the point load. So how to convert? If I just take this section A, B and C. So total total distance is equal to force is 45
Ma'am,
kilonewton
voice
meter.
is breaking, ma'am. Your
Sorry,
voice is not audible. Ma'am, your voice will be not audible for few seconds, then it will be start, ma'am.
is my voice clear now?
Now it is
Is my
clear,
voice
ma'am.
now is my voice clear?
After, yes, ma'am, yes, ma'am.
Okay, okay. So 45 kilonewton meter it is there. So now you need to convert this 45 kilonewton meter to the point load. So this therefore it will be 45 into 8, 45 into 8. So which is acting exactly on the mid span, because always the moment will be maximum at the centroidal distance. So therefore, for the uniformly distributed load, centroid will be exactly at half of the distance. So therefore, it is 8 meter means, so it is equal to 45 into 8, which is acting at the 4 meter distance. So it is 45. So 45 into 8. So 45 into 8, and this distance will be equal to 4 meter from A. 4 meter from A. So therefore, it is 45 into 8 will be this value. So again, if I just take the another last equilibrium condition, that is moment about any of the support, it will be equal to VB into 6. So VB into 6 is going in the anti-clockwise direction. From right side we are considering. So it is positive VB into 6. So next 45 into, so this diagram you just observe, 45 into 8 into the perpendicular distance is 4 meters. So 45 into 8 into 4 meters with the clockwise direction. So it is considered to be as negative. So clockwise it is considered to be as negative from right hand side. So equate that to 0. You will get the value of VB as equal to 120 kilonewton. Substitute the value of VB in this equation. You will get the value of VA as 120 kilonewton. Are you getting these values? Are you getting these values?
Yes, ma'am.
So shall I proceed?
Yes, ma'am.
So next thing is that we are supposed to determine the deflection at C means we are supposed to put the unit load. We are going to assume the unit load exactly at point C itself. So for this also we are supposed to determine what is the support reaction due to this unit load assumed. So here I again consider the equilibrium conditions. So as you know that the first equilibrium, that is a horizontal equilibrium, is satisfied. So the next equilibrium condition is that VA plus VB equal to 1. VA plus VB equal to 1. So upward forces to be considered to be as equal to downward forces. So the next thing is that moment about A I have considered. So here previous to point A you have 2 points, that is VB and load exactly acting at point C. So it is VB into this distance. So VB into this distance. So VB into 6 is acting in the anti-clockwise direction. So from right side anti-clockwise, it is considered to be as positive value. So VB into 6. And again, you have the load of 1 kilonewton. The distance between 1 to VA is 8 meters. So it is 1 into 8, which is acting in the clockwise direction. Hence, it is considered to be as negative. Equate that to 0, get the value of VB is equal to 1.33. You will get the value of VB as equal to 1.33 kilonewton. So after getting this 1.33 kilonewton as the value of VB, substitute here, you will get the negative value of VA, that is 0.33 with a negative convention. Here, the negative sign indicates that VA is in the downward direction. Is this, are you getting the same values, all of you? Are you getting the same values, all of you?
Yes, ma'am.
Shall I proceed? Shall I proceed?
Yes, ma'am.
So the next thing is that we are supposed to determine the deflection. So in order to determine the deflection, we have considered this table over here. So first table is that from A to B. So you can also assume from B to C, CB and BC. So you can assume from CB and BC, or however which is convenient to you, you can assume it. So here I have assumed AB portion and then BC portion. So here, as in case of AB portion, A is the origin, and as in case of CB portion, C is the origin. Why C is the origin? Because we are going to compute the reflection at point C. So therefore, C should be taken to be as origin. Okay. So here I need to consider the limits. So as you know that in the portion of AB, 6 meter is the span. So from A it is 0, at B it is 6. So it is 0 to 6. The limit is 0 to 6. So from CB, so C is the initial point. So it is 0 from C, and 2 meters at B, it is 0 to 2. 0 to 2. So now you are supposed to calculate what is the real moment due to this load of 45 kilonewton at acting at the section of X. Now I just take AB portion here. So this is a uniformly distributed load. This is a, bear with my sketch, please. So this is a uniformly distributed load. I just consider this as uniformly distributed load. Okay. So now this is A and this is B. Okay. So here I just consider the section over here. So EX. Now this is origin is nothing but from A point here. So I need to consider the XX section from A itself, from A which is at the distance of X, not from B. Why? Because origin point is A. So therefore, now I also have the load of equal to VA here, VA. So therefore, if I just take the section, I mean, if I just start with the calculating the moment, so this is equal to 45 kilonewton meter. So if I just proceed it, so starting from point A, so it is VA into X, VA into X. Since it is we are going from left to right, so I just write the sign convention over here. So left hand side, if you are going to take the bending moment, clockwise is considered to be as positive and anti-clockwise is considered to be as negative. So I'm going from left to right. So VA into X is in clockwise direction. So it is positive. And next is I have the load of 45 kilonewton. I have the load of 45 kilonewton. So this is a 45 kilonewton load which is at the distance of X. 45 kilonewton load at the distance of X means, so 45 into X is the point load, and then into X by 2, 45 into X by 2, which is acting in the downward direction and it is going in the anti-clockwise direction. So therefore it should be considered to be as negative. So this value is equal to VA into X. VA value you got it as 120 due to the real load, and 120 into X minus 45 into X by 2. So it will be equal to 45 into X square divided by 2. So is this step clear, all of you? MP calculation for the section X. Is this clear?
Yes, ma'am.
So next thing is that MU1 represents the moment moment due to this unit load which is acting at point C. So here I also take the section. So I just take the section. This is a second sketch. So wherein at this section there is no consideration of the real load. So this is A and this is B. So this is B and this is A. And then I have the section here from B, I mean from A I'm going to take, wherein A is the origin point. So therefore it is equal to X here. So this is moment is equal to VA into X, VA into X. But here VA, I have got it as in the downward direction. So it is 0.33 into X with a negative sign, minus 0.33 into X. So this is the moment distribution as in case of unit load at AB, and I value as in case of AB, here you have 2I, so therefore I have kept it as 2I itself. Is this clear for the portion AB? Is this clear, all of you? Shall I proceed for BC? Shall I proceed for BC?
Yes, ma'am.
Yes, all of you.
Yes, ma'am.
Yes.
Okay. Okay. If I just take for BC, so here BC is the BC. So here you know that C is the point of origin, and you know that it is between 0 to 0 to 2 meters. Now this is the C point. This is a C point of 1 kilonewton, 1 kilonewton load. So if I just only take this part, this will be in the point of, in the portion as in case of cantilever beam. So wherein one end is fixed and another end is free, like that. So here only in this case, if you are going to consider, so C is the origin. So from C you are going to put the axis xx, which is at the distance of x from C. X from C, you are supposed to put the x distance from C. So therefore, for the mu1 it will be equal to this distance. So this will be equal to C point, and here I have taken the x distance, and here I
Ma'am,
have
you're not audible.
taken the x distance here. So x distance. So therefore the value will be equal to 45 into x square by 2. So which is going in the clockwise direction. So which is going in the clockwise direction, hence it is considered to be as negative. So I value here will be I as it is. So now is it clear for portion BC?
Ma'am, will the h be same for both the sides, ma'am? At equidistance from A also from C also.
Yeah.
Is h value same for both the portions, ma'am?
Sorry.
H value, ma'am, is h value same for both the portions? For AB you took h from A, and for C you took h from C. So
For
are
C, I
those
have
both h
taken
same?
X from C. Yeah, why?
Yes.
Because the origin points, both X, it may or may not be same. Because the distance of X will be different for, as in case of different loaded conditions, right?
Yes, ma'am.
Hmm. So
But
now,
while integrating,
uh,
we multiply that, no, ma'am.
yes, we multiply that and we'll get the value X. Okay. So now, after taking this values, we'll get the value of deflection. So first and foremost thing is that we need to integrate this between the values 0 to L, mu1, mp into dx divided by ei. So therefore, what I think someone asked the question, x value is same. X value might or might not be same. Why? Because see here, as in case of integration, we are going to integrate it as a separate entity. For AB, we are integrating from 0 to 6. So for BC, we are going to integrate between 0 to 2. So wherein the X value will be different. Is it clear, all of you?
Yes, ma'am.
So therefore, x value for mu1, as in case of AB, it is minus 0.33 times of dx, and then substitute the value of mp here as 120x minus 45x square divided by 2 divided by 2ei, because I value here is 2i. And the next thing is that integration between the limits 0 to 2, and mp value is 45 x square divided by 2, and then we need to multiply with emu1 as minus x divided by I value remains I itself here, so it will be ei itself. So if you are just integrating that, if you simplify and integrate that, you will get the value as 20 x cube divided by 3 with a negative sign convention, and then 3.75 x power 4 by 4 with the limit 0 to 6. And then this value for portion BC you will get as 22.5 x power 4 divided by 4 with the limit 0 to 2. So after all the simplification, you'll get the value of delta as 135 divided by EI. 135 divided